atoms. Dun, dun, dun. Okay, you don't need your calculator today. Yay. What?
I said good because I forgot it.
Okay, whiplash, right? You don't need a calculator. Okay, so a lot of this stuff seems kind of review. We talked about matter can either be a pure substance or a mixture, and if it's a pure substance, either it will be an element or a compound, right? So actually, I think we talked about earlier the fact that all matter is made up of atoms. Okay, matter can be either a liquid, solid, or gas, but it's all made up of atoms. And basically, compounds are made up of more than one atom of different elements that are stuck together in a repeating unit called a molecular or formula unit. So what this is saying is basically if I have a wand here, if this is my energy wand, and this is my cute little atom sitting minding its own business, I cannot take my energy wand and I cannot break my atom down any further. As long as it's just a normal energy wand, it's not a nuclear energy wand, okay? I can smash this nuclear fission, right? Okay, but we're not doing this. This is a normal one. So we can't break an atom down any farther. So an element is a pure substance that has all the same atoms of the same type. So we have, and I brought my little black and white periodic table. We have a periodic table on the wall. We'll be talking more about the periodic table. Okay. But whichever periodic table you're looking at, each of these boxes is a different element. All right, so I have some kind of cheesy pictures. What's the symbol for copper?
Cu.
Cu, exactly. Capital C, lowercase u. Pictures of copper, trying to look even closer at copper. Okay. Fancy microscopes actually can get a sense of the arrangement of atoms like this. Each little bump would be an atom. This is actually just a figure. If I were to animate this, the thing in the center would just kind of maybe vibrate a little bit, but those little black speckles, for an atom, what's the outside particle that, there's letter E.
Electron.
Electron, yep. Those little black speckles are going to be our electrons, okay, so. All matter is in motion, and it depends upon which physical phase it is and what temperature it is with regard to what sort of motion it has, but I think we looked at this before. Okay, we use symbols. You guys told me Cu is the symbol for copper, the element copper. Cobalt, Co, sodium, Na, iron, Fe, potassium, K. What is the symbol for magnesium? Mg, very good. Got a little geologist over here. What's the symbol for uranium?
U.
U. Just plain old U, yep. What's the symbol for calcium? Ca, very good, you got it. Actually, one of the things I do in my spare time, there's this thing called, I'm smiling because it's just really cheesy. I think it's called Quizlet? Yes. Quizlet, I think it is. Is it a game where you enroll and then you play? Yeah. So there's one for just elements, and you could do that all day long. Okay. So this actually, though, is a new slide. Now, we're going to talk more about atomic numbers. And some of you guys already know this. We're going to talk about actually today. Okay, atomic number, that is the number of protons. The number of protons in the center of an atom of that type of element. Atomic number. And it's kind of solid. Like, here's a periodic table, and if you can see the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, those whole numbers are the atomic numbers. The whole numbers are the atomic numbers, number of protons in the nucleus of that type of element. And they are arranged kind of from left to right. Then you go down a row, go down a row, down a row. Okay, it kind of reads like a sentence. So one of the things that, and I don't, how do I say this? You might want to take a black and white periodic table and let me know if you need a copy, because I think you got a couple copies between your lecture notes and your lab manual. But maybe just highlight where these 1 through 20 are, so that's hydrogen through calcium. And then we skip a few. You need to know 24 CR, what's that the symbol for?
So what did you say?
CR.
Chromium?
Chromium, it is. And so you need to know chromium
There's a
through
good one in the cover of our.
zinc.
So 1 through 20, and then what else?
Yep, all of 1 through 20, 24 through 30,
okay.
35, 36. So these should all be, did you have these on your?
Mhm.
Yeah, okay.
Oh, I thought you were just singling out certain ones.
No, those ones that I was just saying are the ones up here. So, is that the only thing you need to know this semester for the test? No. But like what this slide says, you need to be able to, if I say CR, you need to know chromium. If I ask zinc, you need to tell me the symbol is 2 letters. ZN. Yeah, that's up there. Okay, U for uranium. You need to match up the name of the element with the symbol.
So do we need to remember the numbers too?
No, that's a good question. You don't
If
need.
say 18, you don't need to know. like,
Correct,
18.
that's right. You do not need to know the number, like 18, what is it? I'm like, I don't know, what's a noble gas? Yeah, okay. So, yeah, I'm like, very good, so you don't need to.
I need some clarification. So he's talking about these numbers, or he's talking about the number of protons?
He was talking about the number of protons. Yeah. But on your test, you're gonna get, and I tell students just like this, on your test, you'll have something just like this. But you see what this is missing is the names of the elements. So you'll have something just like this. By the way, and I think, oh goodness, maybe it's been 6-8 months, but we filled in, the physicists and chemists actually filled in the rest of these. So they call this period 7. We're all the way, we have it complete. So ready for period 8, which is amazing. Okay, but to me, I hate the thing, they're like, oh, they discovered a new element. No, they made a new element, okay? These heavy ones, what's that? Not for very long, yes, exactly. So what they do is they use a smash 'em up fission sort of thing. So they basically have one atom gobble up another atom. They join together and they have more protons than either one had individually. But the problem is the stability issue. That thing may or may not want to stay an entity. It has to stay so long before it can go on the periodic table. So when they say they discovered a new element, I'm like, dude, you worked to birth that thing, right? So anyway, that's my...
When you said gobbled up, I thought of Pac-Man.
Yeah, it's gobbled up, that's right. So, exactly. Okay. So I looked in my notes and I thought we talked about this, but I guess we didn't. Okay, so there are 7, and I guess they aren't all gases, but they are 7 elements that are diatomic elements, which simply means under normal Earth temperatures and normal Earth pressures, they like to stick with one of its own. It never likes to be by itself. They're diatomic elements. So we have to use a formula to represent them. So here they are listed in order of lowest atomic number to highest atomic number. So hydrogen's never by itself, it's always buddied up. And I mean, can you make it be by itself? Yes, but naturally occurring, it's H2. Nitrogen, another one, most common gas in this room. Oxygen, fluorine, chlorine, bromine, and iodine. Yeah, iodine is a solid, a pretty purple solid, and actually bromine is one of our 2 liquids. So, but these others are gases. Funny how that is. The heavier they get, the more likely they are to not be a gas. It's kind of a...
This isn't too far off topic, but you usually refer to them as like bromide, chloride, fluoride. Is that in a different state?
Yes.
Okay.
These are all N's.
State meaning location or state meaning? Like
State
form
meaning
of
they're an
the-
ion, actually. The IDE instead of the INE, IDE means it's actually an anion.
Okay,
Yeah, we'll be talking more about that, but INE.
later.
Chlorine, not chloride, chlorine. Yep. So now I don't think you have this slide. This is actually how I learned them. If at the bottom of your slide you want to write this word, HOFBRNICL. HOFBRNICL. That's how I learned my lovely diatomic elements like 50 years ago. I guess it couldn't have been 50 years ago. That would be really bad. But it kind of spells a name, Hoffernickel. And if I put little subscripts 2 there, okay, you have the 7 diatomic elements. Okay, so hydrogen, oxygen, fluorine, bromine, nitrogen, iodine, and chlorine.
Are all of those considered halogens or just the one in?
Yeah, hydrogen's not a halogen, oxygen's not a halogen. Halogens are your 7A elements.
Right, I wasn't
Mhm.
sure if they considered the others halogens as well or.
Nope, nitrogen isn't,
So
nope.
what is the significance of this order, or it's just how you?
Just it's a mnemonic device to me, or is that what I want to say? Anyway, it's how I remember it.
Okay.
Yeah. And actually, the other one I gave it to you was increasing number of protons. So, and this is just how I remember it. Cheesy. I used to have like a little card and everything. So here's where they are on the periodic table. And Christian was asking, are they all halogens? And we'll be talking about this actually in this unit. Certain families, when I go like this is a family of elements. Some of them have a name. And if you look at here, beginning with fluorine, those guys are halogens. Okay, so, okay. So, every science has their fathers. Every science has their scientists that made a lot of headway. And actually, I should also say, oftentimes when scientists make headway, they didn't do it in a vacuum. That's to say science is very much building on what others have done before. Because Democritus, clear back in 300 BC or whatever, came up with the concept of an atom. That's actually our name atom comes from something that he came up with before. But Dalton, in kind of in more our contemporary chemistry, he said that all matter is made up of atoms, and the atoms are indivisible and indestructible. So that's what he originally said. Now, if it's in blue, and I hope you're not colorblind, let me know if you are, but the stuff in blue actually is not correct. Okay? I mentioned this energy one. Well, if you go ahead and do it under certain energetic conditions, you can actually split an atom. You can destroy an atom. So he wasn't totally right about that. So again, we have something that's in blue, kind of blue-purple, okay, mass, okay. So Dalton went on, another one of his tenets, he said that atoms of the same element are identical in chemical properties. So atoms of the same element have the same chemical properties. Atoms of the same element. So all iron atoms behave the same chemically, and physical properties, chemical properties. All sulfur atoms behave the same. That's fine. But they are not necessarily all the same with regard to their mass. And we're going to talk about, some of you are familiar with this idea of isotopes. Isotope is basically you have 2 atoms, the same element, but one weighs different. And I'll go ahead and tell you, the only reason it weighs different has a different mass is because it has a different number of neutrons in its nucleus. So isotopes were kind of where. He went on to say that atoms of different elements have different masses and different chemical properties. That's cool. So Dalton introduced the concept of compounds. So he said compounds are formed by the combination of 2 or more atoms of different elements that are in small whole number ratios. And the words, or the the word small here is incorrect, because if you get into the molecules that build life, okay, you're talking macromolecules, and you're talking lots of atoms. So there are whole number ratios, but they're not small. This last one's got something red, and that red actually was added to his original tenet. Kind of goes back to what I said about nuclear chemistry. Dalton said atoms are neither created nor destroyed, and if you can make that statement correct if you say during ordinary chemical processes, during ordinary chemical reactions. Ordinary chemical reactions are simply you're either taking a wand and whacking maybe a chemical bond between two atoms, or energy is going to be released as bonds are formed. All right. Okay, so in physical science, there's a lot of conservations. And I just want to talk about the conservation of matter here as we're talking about atoms, conservation of matter. Atoms are neither created nor destroyed as long as you have an ordinary chemical process going on. During a process that's ordinary chemistry, atoms stay intact. In fact, some of you are familiar with balancing chemical equations, which we will do. We're going to count on this fact. The atoms that you start with are the atoms that you end with. So atoms of the different elements. So that's kind of nice. So matter is neither created nor destroyed during ordinary physical and chemical processes, and mass is always conserved. So they're all kind of saying the same thing, conservation of matter. Okay, and I've got a little figure here. This is kind of adorable. So this actually is I love chemical equations, because chemical equations describe a chemical reaction just like what might take like 2 paragraphs is done like this succinctly. So we'll be talking more about chemical equations, but you read them from left to right. So here we have silver nitrate and potassium chromate. So silver nitrate, potassium chromate. Silver nitrate is, well, clear. There's a lot of clear things, but actually that potassium chromate's got that pretty yellow color. But notice the scale. We've got 104.50 grams. Go ahead and mix the two, and it makes silver chromate and potassium nitrate. And we'll be talking about how you name those things. We'll be talking about how you kind of come up with this product side. This actually is just an exchange reaction. By exchange reaction, they're kind of fun. So actually it's precipitation and an exchange reaction. Basically, the first part, the silver, if you notice on the product side, it matches up with the chromate. They like switch partners. And this potassium ends up with the nitrate. So we have potassium nitrate and silver chromate. But that's not the point of this slide. The point of this slide is, if you look before and after, a few things. One is the mass is the same. Frankly, if I were to do this in lab, the masses would be a little bit different. They always are. So I'm not really sure if I believe this or not. But the other thing is, how can you tell there's a chemical reaction in the product side? Color change, yep. And if you could actually see that, can you almost see the color change, but can you see kind of the stuff settling to the bottom? That's actually, what does this S stand for? Solid, yep. That S is actually, that is your silver chromate. Anyway, but mass is conserved. All right. So, the law of multiple proportions. And the example I have is carbon monoxide and carbon dioxide coming up. If you read it a few times, it simply says if you have 2 elements that are forming multiple compounds, like CO and CO2, 2 different compounds, then you should be able to kind of backtrack with regard to relative amounts. Okay? So this is what I mean. If we consider carbon monoxide and carbon dioxide, they both have carbon oxygen in them. Okay? This simply says if you let the mass of carbon be equal to 1. Okay, here we have a relative amount of oxygen of, wait, how do I say this? The relative amount of oxygen in carbon monoxide relative to carbon dioxide is 1 to 2. If we let our carbon be fixed, then our oxygen in the two compounds has to be, relatively speaking, 1 to 2, because we have CO and CO2. So anyway. All right. Here we go. Now, if you take, and I don't know, I guess it would be a normal college physics class. It's been so long ago since I took college physics. But they will actually talk about atoms being made up of smaller particles than electrons, protons, and neutrons. But these are the only ones that chemists really worry about. And these are the only ones we need to worry about.
Electrons are shut down.
Yeah, that's true. They're a primary particle. So we need to kind of know our way around those 3 particles. Now, 2 of those particles live in what's called the nucleus. And I didn't bring it with me today. I have a BB, or some BBs in the lab. But if I were to put a BB on the floor, I'm reading this caption down here, okay? And then I'm going to go 10 stories. If a story is about, 10 feet maybe? I don't know. Each, like, what's this? To the ceiling. 10 feet, okay. So if I was going to go, I'd have to go 100 feet high, okay? And that's actually, my BB is the nucleus, and 100 feet away from it, that's kind of where the electrons are hanging out, or the edge of where the electrons are hanging out. So BBs, relatively speaking, the size of the nucleus, go up 100 feet, and a sphere, 100 feet in all directions. And that's kind of what we have going on. Now, nuclei are a lot smaller than a BB. So that's kind of where the scale comes from. And this is where sometimes students will say, wait a minute, the electron, or the electron cloud, which is kind of this fuzzy yellow stuff, the electron cloud, I could like step through that, right? And I'm like, in theory. So honestly, an atom is mostly empty space, volume-wise. So, but if you're like me, you've probably heard this before too. The reason atoms, the nuclei don't pass through the electric cloud of another one is because of the electrostatic repulsion between them. So it's cool. It's so interesting. So now I have a slide for each subatomic particle. Subatomic particle, starting with the protons. First off, remember that we already know something about the protons. That actually is their atomic number. If you want to put atomic number, that would be great. The top there. And I should put atomic number. The symbol for atomic number, it's coming up actually. This is what drives me nuts. Don't blame me. It's the symbol Z. Now, in order to differentiate my Z's from a 2, this is how I learned it. I put a little thing through it. So that's my Z, atomic number Z. Think of like World War Z. Okay. So they're positively charged. They're found in the nucleus. There is an attraction between the protons and the electrons, so actually they're kind of helping the atom stay together. Protons and electrons have an attraction for each other. They hold electrons there. And of the 3 subatomic particles, and I have a little table to show you this, of the 3 subatomic particles, only 2 of them have significant mass. They're the protons and the neutrons. So the protons bring a mass to the atom. The last one simply says, and I hope we're all going to be kind of on the same ballpark with this, the number of protons in the center of an atom define what element that atom is. I won't say when it grows up. No, it's already grown up, right? So that's just to say, for instance, if I just randomly say, copper, it has 29 protons in its nucleus. Okay. If you've ever heard of like alchemy, like I know it's kind of silly, But like if you wanted to turn silver, okay, silver's Ag, what's the symbol for gold? Au, yep. If you wanted to turn silver into gold, they have to have 47 protons, that's what you'd start with, silver, and you'd need to somehow get up to 79 protons for gold. Okay, so it's not happening. All right, so that's kind of how that works. Okay, so that was protons. Neutrons, the symbol for neutron, neutron is an N with a superscript 0. It's actually neutral. Symbol for proton was P with a plus, means it's positively charged. Neutrons are also found in the nucleus. Neutrons allow the protons to coexist. It simply means, like if we pick on carbon a lot. Carbon, it has 6 protons, and a really common version, isotopic form of carbon, has 6 neutrons. So if I look at my nucleus, okay, I made 6 pluses. Now, oppositely charged particles attract, same charged particles repulse. So these are not going to want to stay there. We're lucky that one of the things, the way I look at it, that the neutrons do, and I've made them now as 6 zeros for neutrally charged neutrons. One of the things that they do is kind of allow a little bit of space between those positively charged protons. So they help them coexist. And then the last one here is something we saw with regard to protons. Like the protons, the neutrons have significant mass. Now, in chemistry, we say electrons are basically massless. I'm laughing because physicists probably would just go through the roof with that. Okay, so we're actually going to say electrons are kind of, they don't have any mass. And we're going to introduce a new mass scale, which is going to be an AMU, atomic mass unit, and we're going to say protons and neutrons are both 1 AMUs. Isn't that nice? Great. Okay, so on to the last one. Electrons, an E with a superscript negative sign, are negatively charged. They're found in a cloud outside the nucleus. According to somebody whose name became famous with Breaking Bad, any Breaking Bad fans in here? Okay, Mr. Heisenberg. Okay, Heisenberg's uncertainty principle says you cannot know both the location of an electron and its energy at any given time. Heisenberg's uncertainty principle. So electrons are what give an atom the volume it's going to have. And you kind of saw that with the BB and kind of the 100 feet in all directions. You know, if 100 feet in all directions is the size of my atom scaled up, and the BB is my nucleus, then all that other stuff is my electron. So it gives your atom volume. We'll be talking more about the sizes of atoms, so it's electrons that give the atom volume. And when we start to talk about compounds, I'll just show you an example here. So, for instance, water, you guys, I think have told me before, is 2 hydrogens and 1 oxygen. Okay. So I'm going to go ahead and put my oxygen here. I'm going to put a little line here leading to my hydrogens. And I'm going to go ahead and say that actually is a chemical bond, CHM bond. My point here is that chemical bond is all about electrons. Electrons being shared, electrons being transferred. When I take water, H2O, and add a current, I said before, I think you can break it down and it can go back down to its elements, H2 and O2. Okay, and actually it's about electrons going their individual way there too. So there's no animation. This is just a figure. The Christmas tree looking thing. What are the 2 colors?
Red and green.
Yeah, red and green, and the 2 colors represent protons and neutrons. So I mentioned the Heisenberg's uncertainty principle about where an electron is. One of the things I'm going to try to well, we'll end up talking about when we talk about electron configuration, is if my fist is the nucleus of an atom, it's not like the solar system and where electrons go around like this, you know, like we know where the Earth, how the Earth is going to orbit the sun, okay? Basically, what happens is the electrons reside in a domain called an orbital, and it's a space where there's a variable probability of finding the electron. So anyway, we just kind of show it as a cloud, electron cloud. Okay, don't have anything, my animation's not working. Okay, so here's a table. The first two columns just talk about charge. Okay, so I bet you guys are fine with this. The protons are positively charged. With regard to, on the atomic scale, we're just going to say protons are a +1. Neutrons are a 0. Electrons are a -1. So does this make sense? Well, I'll just go over here. I started to draw my carbon atom over here. I'll add to it. Carbon, if you find it in the periodic table, is atomic number 6, so it has to have 6 protons. We're going to talk about this here in a minute. Neutrons are kind of like Mother Nature's spice. It can kind of come and go, okay? If this is a neutral atom, and we'll talk more about what that means, you know it's a neutral atom if I don't have any charge up here. No charge, it's free. No charge, question mark, that means it's neutral. If it's neutral, then the number of electrons have to be equal to the number of protons. That's it. And I kind of mention that because if I was to kind of, I'll go ahead and do my, okay, so I know they're arranged better than that, but there's my 6 electrons in a cloud outside my carbon nucleus. I could say I have 6 protons, and I have 6 electrons for a net charge of 0. So that's all that is, a neutral atom. So I mentioned masses. Now, you probably already had an idea how small an atom is, okay? So the stuff that makes up an atom must be very light. So on an individual basis, an individual proton will weigh, in terms of grams, 1.6726 times 10 to the -24th grams. Notice that a proton and neutron are very similar. And then off by magnitude of 4 are the electrons. So to me, you're like, well, they're all light. But here's where it goes. We introduce in chemistry a new mass scale. So instead of grams, if we talk about AMUs, atomic mass units, and if you want to, you're going to have to kind of work with me because growing up, I learned it as not the symbol U for AMUs, but the symbol AMU for AMUs. So when I say AMUs, atomic mass units. And for those of you who are wanting to link it to something, I'll go ahead and tell you. Let's see, how's this work? No, I'm not going to tell you in case I witch that. But there's a, I call them AMUs. Your book uses the symbol U. So that's the units. My point here is going to be, if you look at the protons and the neutrons and compare that with the electron. And that's where I say it's generally massless. That's where I'm going with that. Okay. All right. So, atomic number. Remember kind of back to the slide that says know these elements by atomic number. It's the number of protons. It is the symbol Z. Don't blame me. And all this is saying is kind of like the example I have up here. If you're dealing with a neutral atom, and how do you know it's neutral? Well, if somebody doesn't say it's charged, then it's neutral. How's that? The charge, if there is one, will be kind of this upper right-hand corner. If it's neutral, then electrons are equal to number of protons. That works. Okay, so we have atomic number, and then we have mass number. So the two particles that have mass are in the BB. The two particles that have mass are in the nucleus. What are they? Protons and neutrons. Mass number is, let's see, how do I say this? Well, the symbol is A. This is where it seems like A they should have used for atomic number, and Z they should use for mass number. But if you're like me, I just always have to think backwards. Atomic number is Z, number of protons. Mass number is the variable A, capital A. And literally you are counting protons plus neutrons. So let's go over here. Let's just knock this out. So I got Z. What's my Z here?
6.
It is 6. Number of protons. Awesome. What is my mass number?
12.
Why is it 12?
Because you do the protons and
Yep, it is 12. Yep.
Yeah.
Number of protons plus number of neutrons. Yep, you got it. That's it. I know, you're like, really?
Will we do anything with binding energies in this class or not?
No. Guess you have to
So
take a
boring.
different, well, take a different class. I don't know if you need this one or not.
Where do you start doing that stuff? Nuclear
If you look in
chemistry and,
Petrucci, like, I think chapter 19.
But we won't do it here. So where in, like, a college degree would you start doing that? It's like junior level, senior level, master's level? What is that?
I'm trying to think. I think I studied it in physics, but
So it's not really.
I don't
really
remember.
applicable.
I don't remember. I'd have to think about it. I'll think about it, but
All right.
yeah. Binding energy actually comes when, I said the word transmutate, or anyway, nuclear chemistry, when you have something radioactive or something like that. Yeah. So, sorry. Okay. So atomic number of protons, is unique for an element. Okay, that makes sense. Okay. Atoms of different elements will have different atomic numbers. But into jada. But mass number for a particular element is not unique. Okay? So that goes two ways. Actually, atoms of the same element can have different mass numbers. What's that mean? Well, that means that you have the same number of protons, but you vary in neutrons. Nature's sort of spice. Okay? And you can have atoms with different numbers of protons, so they're different elements, but they can match up with regard to their mass number because you kind of sprinkled back the appropriate number of neutrons. So you can have different elements share the same mass number. Makes sense? All right. So all of this different mass number, same element sort of thing leads us to the important concept of isotopes. So that's all an isotope is. There are various isotopic forms of the same element that all they differ in is the number of neutrons. Now I kind of teased that Mother Nature can kind of sprinkle in neutrons or remove neutrons at will. No. There are very stable forms that it will or won't allow. The stability of the atom is in question. So isotopes are atoms of the same element that have different masses because they differ by the number of neutrons that are present. So if they differ by the number of neutrons present, then they differ by their mass number. Isotopes. So, for instance, this, or maybe it's on the next slide. Oh, it's coming up. This almost sounds like an oxymoronic statement, phrase, or whatever. There is one isotopic form of these guys. So these are 1, 2, 3, 4, 5, 6 elements. You probably recognize what they are. 6 elements that in Mother Nature only has one way of doing business. But do you know what I'm saying? Like isotope, it seems like you should at least have 2 forms of one. Okay, so these are examples of elements that have 2 naturally occurring isotopic forms. And these have 3 or more isotopic forms. I didn't bring, but I'll try to remember to bring Wednesday. A lot of times, if you get like one of those quick study guides sheets, like for chemistry, okay, that's like everything on it. A lot of times, it will have the elements kind of listed out, and it will say, it's like hydrogen, and the 2 naturally occurring isotopic forms, and maybe even a 3rd isotopic form, and its relative abundance. How close are we to? Thank you.
It's a little ways off.
We are a little ways off.
We're halfway through.
Thank you.
For that last slide, will we need to know that, like memorize those?
No,
Okay.
no, you won't. Yeah, you will not need to memorize this. And I will give you isotopic information when you need it. And there is a certain problem that you definitely have in your test with isotopic information. We'll talk about that. It's just how do you come up with the average weight? My gosh, if you have, for instance, carbon, multiple forms of, how are you supposed to know how much a carbon atom weighs? And we're going to do a problem like that on Friday, based upon. So picking on carbon, you guys told me that the mass number is 12 here, okay? So actually, one isotopic form of carbon is what we call carbon-12, okay? So we can write it carbon-12, C-12. We can do the symbol for carbon in the upper left-hand corner is the mass number. That's protons plus neutrons. Here, this is a little bit redundant, and this actually is a form we'll be talking more about on Friday. The symbol of the element, the mass number for that particular isotopic form of the element, and 6 is redundant, because if you got a carbon, if you know it's a carbon, 6, by the way, is the number of protons. You're like, I know that. Okay. So one last thing for today. Have you heard of carbon-14 dating? Okay. So carbon-14 is just another of the elements carbon, another atom of the element carbon that has 2 extra neutrons. Excuse me. Instead of carbon-12, it's carbon-14. Okay. So I'll put 8 neutrons, and that will get you carbon-14. We good with that? So the thing about carbon-14 is that it's not as stable as carbon-12. Carbon-14 actually, for all living organic animals and plants, we incorporate carbon-14 on a daily basis. So the thing is when we die, when we cease to be living, we are no longer going to incorporate carbon-14 into our bodies. In fact, carbon-14 is gonna start a well-known decay process. So the thing is, to understand if something was once alive, to understand how long ago it was living, what they do then is go back to see how much carbon-14 there is remaining in the tissue of that biological organism. It's called carbon-14 dating. And actually, if you take general chemistry 2, we'll talk about that decay process. We'll talk about how it's measured.
So I have a question, this might not be related, but just about that. So does everything have the same amount of carbon-14 in it? Like, so if you're dating something that you think is 1.5 million years old, would you first need to know how much carbon-14 was in that specific thing to measure what it's at now to know how old
You
it
can
was?
assume that it was incorporating, had a certain amount, ratio of carbon to carbon-14 in as it was alive.
Okay,
So you,
so like a bone, let's say like a dinosaur bone would have the
Mhm.
same amount of carbon-14.
well, it would have less in it now than
Well, no, yeah,
something
that
new,
does
yes,
not, but
yeah.
how, like, you
The
have to-
ratio, you go the regular carbon to carbon-14, that ratio that's remaining.
Okay, I
And
was
it's
just
a,
curious.
it's a clock ticking down.
Cool.
Does other things, change that, like weather elements throughout the year?
No. Nope. It's an isotopic decay thing.
Is it kind of like thinking of like, when they talk about radiation and they talk about half-lives, it
Right.
takes so long.
Yeah, it's definitely a
It's-
half-life thing, yeah.
Okay.
Yep, yep. Okay, well, we did not get to an assignment slide. I hope this works for you. In case, actually, since we don't have a normal Wednesday study session, there won't be anything to hash out that way. But there'll be an assignment definitely on Wednesday through Friday that you might have questions for. Okay? Sweet.
So it's a ratio